We invite our next speaker, Dr. Gauri Srinivasa. Dr. Gauri Srinivasa is a professor in the Department of Information Science and Engineering at PESIT Bangalore South Campus. She obtained her bachelor degree in Computer Science and Engineering from PES Institute of Technology at Bangalore in 2004. She obtained her PhD in Biomedical Engineering from Carnegie Mellon University in 2008. Dr. Gauri's research interests are in the area of image and signal processing, multi-resolution techniques, and pattern recognition. Dr. Gauri is an associate member of Technical Committee for Bioimaging and Signal Processing of the IEEE Signal Processing Society. Ma'am, it's our pleasure to have you here. We welcome Dr. Gauri.
My thanks to Saha and Dr. Geeta Manjunath for having me here. So we're talking of eloquent poetry over here by way of deep vision, and my task is to teach you the alphabet, so to speak. So this is generally a semester-long course that I've just tried to cull out very important points. So everything here is debatable, what is important, all the way to what is computer vision itself. So this is the most cliched thing that is said when we talk of image processing or computer vision. A picture is worth 1,000 words. So these are, some really interesting pictures that would take a lot to describe. And some pictures are worth more than thousands of rupees as well, as we had people waiting to see them. So how exactly, what is computer vision, or what does the computer see if we have an image? So this is a color image, and if we think of this as being made up of components of red, blue, and green, these are colored, for effect. So what the computer really sees from any one of these is an array of numbers. For us to go from this to all the wonderful applications that we've been hearing about, it is a long jump. So looking at how people traditionally thought of coming up with making sense of these numbers, the first thing that people asked is, if we care about what is in the image, does the color even matter to us? So starting with the color image, can we look at a grayscale representation where maybe we simply average out the components of red, blue, and green and obtain just one number for each pixel location, or pixel is a picture element. Each entry in that array that we saw earlier is a pixel. So we go from color images to grayscale. And when we look at grayscale images, earlier we used to say black and white televisions, color TVs, and so on. So is grayscale the same as black and white, or is it something else? So clearly, if we set a threshold or a rule to say if the pixel value lies between certain intensities, then it is white, otherwise it is black, for example. So we might end up with this representation, which is truly black and white. There is nothing in between. So why is this important? If we are trying to segment out something from this, for instance, so if you're trying to look at perhaps, trying to get out something that is really interesting from the image, maybe a portion of the necklace itself, or maybe the people, the faces, and so on, we might want to look at a simpler representation than a grayscale image. So this process is known as thresholding, and you can think of this as traversing the two-dimensional array and checking with the rule whether the value of the pixel lies in this range. So we don't have to think of just setting one rule. We can have multiple rules, so we can have multi-levels of thresholds and obtain multiple regions that are homogeneous or conform to different levels in the grayscale. Looking at these pixels, what if we wanted it to be brighter or darker? So for whatever reason we want to enhance the image, we can apply more such rules. So one of the easiest ways to do that is to summarize an image using what is known as a histogram. So a histogram is essentially a count of how many pixels lie in a certain range. So if you're looking at listing out all the possible pixel intensity values, if it is an 8-bit image, the intensity values would range from 0 through 255. And for each of those, we would traverse the array and check how many zeros, how many ones, twos, threes, and so on. So that is the plot, that is the histogram. And to make the image brighter or darker, we study this histogram and decide what sort of a transformation to apply. So what we see on the right hand side is, if there is a certain level of the input gray, what should it be mapped to in the output image? So it's a grayscale to grayscale mapping. An identity map would take a 0 and map it to a 0 in the output, take a 255 in the input, map it to a 255, and essentially everything is where it stands. So this is like the x is equal to y kind of a map. And the negative would take a 0 and map it to 255, and take a 255 and map it to 0. So this inverts the black and white, and everything else in between here. So the log transforms try and take values. So if the image is dark, it tries to spread out smaller values through a larger range. This is called range expansion. The consequence of this is brighter values are automatically crushed into a smaller range. So there is a range compression that automatically happens. The range expansion is for darker intensity values, and range compression would be for brighter intensity values with the log. And if we have a very bright image that we want to reduce the brightness for, we would apply the anti-log or the exponent transform. So that would do exactly the opposite. So that would try and compress the range for darker values and increase the range or stretch the range for brighter values. Similar to the log transform is our nth root, and similar to the exponent is the nth power. So these are the common transformations that can be applied. And here you can see that the histogram for a dark image is in the lower intensity values. The histogram for the bright image is more populated in the brighter or larger intensity values. So what we would like to do is apply a transform that will spread this or stretch this out. We can also look at contrast stretching. So we can say, we can apply these transformations not from 0 through 255, but through between specific intervals of gray levels to increase the clarity of what we see. So we're not obliged to necessarily stretch the transform from 0 through 255. And one of the ways of doing this is what is known as histogram equalization. So given a dark image or a bright image whose contrast we want to enhance, we could simply say that the histogram should be spread through all the values, and this would increase the separation. So whatever is concentrated only in the dark intensity values now gets spread throughout the entire range of grayscale. So without explicitly studying the image or looking at what parameters to tune for a log transform or the exponent transform, we can easily apply this histogram equalization to achieve the same end. And the way that is done is to look at how many to look at the histogram again and try and divide it up into equal intervals. It so happens that if we look at the histogram as a probability mass function, then the equivalent cumulative mass function of that image is the transformation that needs to be applied for histogram equalization. So moving on. So this is an example of how histogram equalization improves the contrast. This is what we saw earlier with the dark image, and most of the pixels are concentrated in a small portion of the entire grayscale. That is stretched through the entire grayscale with histogram equalization, and we didn't really think this through in terms of, we didn't decide what is the log transform or what parameters to use for the nth root transform and so on. We simply equalized the histogram and achieved a very nice contrast with the image. So these are dealing with histograms. Can we do a little bit more? Can we look at blocks of pixels and try and do something with them? So this brings us to designing filters that enable us to do a bunch of things. The first of these that we look at is correlation. In a couple of minutes, I will tell you why we spend a little bit of time on these. So correlation looks at how similar is a mask to an image. So essentially, we're going to place this 3 by 3 mask on top of every pixel here in the image and look at inner products. That is the result of the correlation. So I have a bunch of slides here that are walking us through the entire computation. So we have the correlation output. Ideally, correlation is high if whatever pattern we're looking for is found in the image as is, and correlation is low if there is no relationship between the pattern we are looking for and what is contained in the image. So these are examples of how correlation helps us. If we have templates of what we're looking for instance, we're looking for V in Java, this would be our correlation mask, and we would run this over the entire image, and hopefully the highest match is when this V is centered on the V in Java. So there are a lot of questions that can crop up. A lot of things about when we design templates, are we expecting the same size of the template, the same intensity and so on to be present in the original image? So we can think of different scalings, rotations and so on to make sure that this actually works. The other slightly more complicated cousin of correlation would be convolution. The process is the same, except we flip the filter before we apply the inner product to the filter and the image. That is, we look at the filter and we flip it about its origin. So this is equivalent to sort of turning it over to the left and lifting it up, so to speak. And the process is pretty much the same. Just like we did with correlations, we're looking at inner products to achieve the final output. This is a really important operation when we talk of filtering, and we will see why filters are useful. But just a small caveat for those who know these two operations and are familiar with convolutional neural networks, you will realize that it should have been correlational neural networks, because we really don't flip anything over there. So CNN is correct, but that C is actually correlation and not convolution. It really doesn't matter, but for those who do get it, we can't call it correlational filters, but really that's what's happening. And it also helps us understand why it works the way it does. So replacing the filter that we looked at earlier with a box of just ones, for example, we can achieve some sort of smoothing. So these are different sizes of the filters that have been applied to the original image. Using a 5x5 filter, we obtain this image, and using a 15x15 filter, going through the product, inner products, we obtain this image, and an even bigger filter of 25x25 gives us a smooth version that looks like this. So essentially, these filters are smoothing out the image or blurring the details. So it's taking away details and leaving us with a smudge, so to speak. So how would this be useful? We can look at applications where we're not interested in minute details. We want to pick out the overall, what's going on with the image. So maybe if I needed a head count, I don't really need all the details of the birds, perhaps, some sort of, like this image may be good enough. For image compression applications, this is extremely useful. And there is another whole Pandora's box when we talk of denoising. So if there is a lot of noise for us amounts to details. Blurring out the details is denoising. So here's an example where instead of using filters with convolution, we have median filter. This is a rule-based filter. So the rule is as simple as saying if it's a 3x3 median filter, in every 3x3 patch, look at what the median value is in the image in that 3x3 neighborhood and replace the central pixel with the median of its 3x3 neighborhood. So 8 neighbors and itself, we order all of them in ascending order, look for the median, and the pixel simply is replaced by the value of the median. So this helps us get rid of salt and pepper noise or short noise much more effectively than smoothing it out with a convolution filter. So if we can smooth images, can we sharpen them? Of course, that should be possible. A very sort of traditional sharpening method would be take the original image, use some scaled version of the smoothed image, subtract it out, what is left should be a sharper version of the image. So image minus smoother version should leave us with a sharper version. And these are sort of examples of different extents of removing the smooth version of the image to obtain sharper images. We looked at convolution and finding inner products. There's a really simple alternative to filtering with the frequency domain. We can simply take the Fourier transform of the original image and Fourier transform the filter. All we would have to do then is to pointwise multiply the two. So we would essentially treat the filter as a mask applied onto the image. And of course, we would have to inverse Fourier transform this to get the original representation. So all that we did with convolutions, that is flipping and running over to get inner products, so lots of multiplications and additions, this is a much simpler process when we just look at it. But of course, it involves taking the Fourier transform and inverse Fourier transforms. There are fast algorithms. And as I started with saying, some can debate on what is computer vision. So this is starting to border on what people would argue is image processing. So we will sort of sidestep this entire thing. There are very interesting problems when we look at it for feature engineering. So if we Fourier transform the image, we're looking at frequencies and wiping out all the spatial information. So we can look at trying to look at smaller blocks in space and look at its frequency representation to get a space frequency domain. And this opens up a whole lot of possibilities with wavelet transforms and wavelet decomposition trees and wavelet packet trees and so on. So the whole reason we're doing all this is to move towards image understanding. One of the important steps towards that is to separate out objects of interest from each other and the background. And that is what is segmentation. So ideally, if there are a bunch of objects that we care about, we should be able to identify them and know that whatever is not the object is the background. So to do this, what defines an object, the simplest understanding of it would be the edges, the contours, or the borders. How do we find that? Edges can come about as an interface between light and dark regions or light and dark intensity regions. It could come about whenever there is a curved surface. It comes about whenever there is a shadow effect, or maybe when one object lies in front of another, so there is some sort of an obstruction. So all of these create borders or edges, and trying to find those would help start identifying objects within the image. So here's an example of looking at only the horizontal edges, vertical edges, and this is a combination of horizontal and vertical edges. Looking at edges, so we saw smoothing was applying the convolutional filter with all ones, for example. Essentially, it was averaging out pixel values. So here we are differencing pixel values. We're looking at where is the intensity dissimilar to the neighborhood. So if there are a bunch of light pixels and then a bunch of dark pixels, looking at the differences between neighboring pixels, there will be a point at which a light pixel and a dark pixel are next to each other, and at that point we get a significant difference. So these are useful again for finding structures, and if we said that smoothing is done to remove noise, it's quite possible that with differencing we pick up the noise. So a common technique used to overcome this is to smooth an image, not too aggressively, to get rid of small discontinuities in the image, or what we would call noise, and then apply the differencing operator to get cleaner edges or segmented regions. So why are edges useful? Because ultimately we want to be able to connect these lines that we get and identify some sort of an object that is of interest to us. So how do we connect these? We only get lines after edge segmentation.